Let's talk about simple linear regression. Let's say you would like to model the grades of the students in mathematics as they are related to the number of hours of studies. You gather some observations and plot them using scatter plot. Now, based on the distribution of the points, it seems like there is a straight line model that can best fit this data. We call this line as the regression line. Now, let's recall that in algebra, the equation of a line is in the form y equals mx plus b, where m is the slope, b is the y-intercept. Now, in the language of linear regression, the notation is y cap equals b naught plus b sub 1 x. Why is that so? Now, whenever we estimate a value in statistics, we use this notation cap. Then, the use of b naught, b sub 1 is in anticipation of multiple regression analysis. That is because in real life situations, this grade of students in mathematics is not just a function of one independent variable, but so many other variables. Not only the number of hours of studies, but it could also be the IQ, the socioeconomic status, and so many other factors that you are considering in your studies. And therefore, in multiple regression analysis, this b sub 1 could be extended to b sub 2, x sub 2, b sub 3, x sub 3, and so on, where x sub 1, x sub 2, and x sub 3 are the variables, b sub 1, b sub 2, and b sub 3 are the magnitude of the influence of those variables on the criterion variable value. However, in this video, we are just going to focus on the simple linear regression. In the simple linear regression, there is one criterion variable or dependent variable, and there is one independent variable. Also, in linear regression, the data must be continuous numerical data. If your data are nominal or ordinal, we use logistic regression instead of linear regression. Now, in our notation, this b sub 0 is now our y-intercept b, and the slope m is b sub 1. In this graph, this b sub 0 is the point of intersection between the y-axis and the regression line, and this b sub 1 is the slope. That means that is the ratio of the change in y over the change in x. So b sub 1 is the slope. Now notice that the actual observations are not exactly on the regression line. That means there are errors. For example, this point here is a little bit above the regression line, whereas the second point is below the regression line, and this point is further away from the regression line. This distance is what we call as the error. There are errors above the regression line, and there are errors below the regression line. And one property of this regression line is that the sum of all the errors above and below that line would result to 0. And we do not want to always get a 0 error. We would like to quantify what is the value of the error. And so mathematicians have devised a way to make negative errors positive by squaring those errors, because when you square a negative number, that would result to a positive number. And you would like to minimize the error by getting the least of those squared errors. So we do not want just any other line, but we want the line that can minimize the squared errors. Another term for errors are deviation from the mean or residuals. We would like to minimize all these deviations from the mean. So our choice for that regression line is that that must be a line that will produce the least squared deviation from the mean. To make that concrete, let's say we have this example. For 1 hour of study, the grade in mathematics is 80. For a student who studied 2 hours, his grade is 83, 3 hours 88, 3 hours 90, 4 hours 94, 5 hours 96, and 6 hours 99. Our goal is to model this data using simple linear regression. So let's construct the scatter plot. In the horizontal axis, we have the number of hours of studying. In the vertical axis, we have the math grades. So 1 hour of studying resulted to a grade of 80, 2 hours, 83, and so on. When we say we are going to model this distribution by a regression line, we would like to find that equation of the line. And that equation of the line is in the form y cap equals b naught plus b sub 1 x, where b naught is the y-intercept, b sub 1 is the slope. And the formula to find the slope is n times sigma xy minus sigma x times sigma y all over n times sigma x squared minus the square of sigma x. And the formula for the y-intercept is sigma y minus whatever is your computed slope times sigma x all over n. So in order to apply this formula, notice that we need the summation of xy, the summation of x, the summation of y, and the square of the summation of x, and the value of n. So let's prepare our table so we can find all this required summation. We need to add 2 more columns, and we are going to add 1 row to get all the sum of each of these rows. So we need the column xy. That means that if you let the number of hours of studies to be x and the grades to be the y variable, then x times y means you are going to multiply each of this pair of values row by row. And for the x squared column, we are going to square this first column. So let's perform now the computation. 1 times 80 is 80. 2 times 83 is 166, and let's continue the multiplication. Then for the x squared, you square 1 to get 1 squared or 1, 2 squared is 4, 3 squared is 9, 3 squared again is 9, 4 squared is 16, 5 squared is 25, and 6 squared is 36. Then, let's get the sum of the column x to get sigma x, get the sum of column y, get the sum of the column xy, and get the sum of this column x squared. Then we now perform the computation of the slope. So our n is 1, 2, 3, 4, 5, 6, 7. We have 7 observations. Then sigma xy is 2,230. This is sigma x, which is 24. Sigma y is 630 all over n, and again is 7. Sigma x squared is this 100 minus sigma x is 24, and we square that. From here, we just perform the necessary computation. 7 times 2,230 is 15,610. 24 times 630 is 15,120. 7 times 100 is 700. The square of 24 is 576. Subtract the numerator and subtract the denominator, and divide the results to arrive at b sub 1 equals 3.9516129. As much as possible, we do not want to round off this value because we are still going to use this in our computation for b naught. So this is now our slope. Then computing now for the y-intercept, sigma y is 630. This b sub 1 now is whatever is the result here. Then sigma x is 24, and n is equal to 7. Then simplifying the numerator, that resulted to 535.16129. Again, we do not want to round this off immediately, then over 7. And finally, dividing these two numbers, we have b sub 0 equals 76.451629. So we now have the value for b sub 1 and b sub 0 that we need in order to model this distribution using linear regression. So our model therefore would be y cap is equal to 76.45 plus 3.95x. We now round this off to 2 decimal places. The same thing here. This is now our linear model. And this is now the equation of this blue line. That is now what we mean by modeling the data using linear regression. The regression line is this blue line, and the equation of that blue line is now our linear model. Y cap equals 76.45 plus 3.95x. Here, x is the number of hours of studies, and y is the grade that the student can get. This means that since the slope is 3.95, every additional hour of studying can increase the grades of students by about 3.95 points. This y-intercept also indicates that a student who does not study, that means x is 0, can expect to get a grade of a barely passing score of 76.45 based on our model. Of course, different models can result to different values. Now, regression analysis has 2 functions. The first one is to quantify the effect of the independent variable on the dependent variable. In our case here, the effect of the number of hours studies is that for every 1 hour of additional study, there is an increase of 3.95 points in the math grades. The second function of linear regression is to extrapolate or predict the value of the dependent variable based on any given value of the dependent variable. But notice that in our case, there is a maximum grade of 100, and so even if we continue increasing the number of hours, we know that the grades would not be more than 100. And so every model has its own interpretation. And not all the time the model is linear. It could also be exponential, it could be logarithmic, It could be quadratic or any other functions that you already study in your Algebra 2. In the next video, we're going to talk about the multiple regression analysis and then the logistic regression model. So thank you very much. This is Lando Assistant, and we hope to see you again in our next video. Bye for now.